So, yeah, I want to start by thanking the organizers for inviting me here. Is this working? Yes. Okay, so it's really nice to be back at ITAMP again and to see so many familiar faces. So what I'm going to be talking about is manipulating molecules with quantized light modes and why that means that we have to solve coupled electronic, nuclear, and photonic dynamics. So just a short outline. I'm going to give quite a long introduction and motivation because I think this is something that most people here are probably not too familiar with. So I want to explain why I think this is really something that is interesting and that deserves kind of a lot of attention in terms of the work that we need to do computationally. I'm going to talk about kind of what are the requirements for theory and simulations that we need to take into account, all of the effects that we need to take into account here, and what we are currently working on in terms of numerical methods mostly to solve this kind of system. So the basic idea is we all know if we want to get strong light-matter coupling or influence matter with light, what we usually use in the experiment is a laser where we have many coherent photons. But as an alternative, you can think of kind of making a single photon strong by confining it in space in a cavity, as is done in cavity QED in atoms for many years already. And if I do this with molecules, well, it's basically the same thing. I just have to I have to take into account losses, and here they become very important because my system is extremely lossy in that sense, some sense. So if I look at the simplest model of some kind of molecule inside a cavity, and for now I assume it's a two-level system, we're going to relax that later, of course, and I say, okay, this is a molecule with some excitation energy, and then the photon energy of the cavity is the same. I can write down kind of as the simplest model a 2x2 Hamiltonian, which is just the coupling between the dipole that the molecule has in the excited state, or the transition between the excited and the ground state, and the cavity photon. So the coupling that you have here, G, is just the dipole moment of the molecule with the field of a single photon in the cavity, and that scales with 1 over the mode volume of the cavity. And then the only other kind of maybe not completely standard thing is that for this simple model, I'm going to include here losses both of the molecule itself, which can be dephasing, and also radiative decay and non-radiative decay, etc. And for the cavity, which leaks out through the mirrors. So if it's a metal mirror, it also has losses inside the mirrors. So if I diagonalize this is basically trivial. I get, in this case, the energy back plus the average of the losses, and then I get this interesting square root term where I have the coupling squared minus a term including the losses. And this is exactly kind of where I can do the distinction between weak coupling and strong coupling. Weak coupling means the coupling here, the G, is smaller than this loss term, and then what I'm really doing is I have a negative part inside the square root. I get a small modification of the imaginary part of my energy, so I'm modifying kind of the loss rate of my system. I'm modifying, if you want, radiative emission of the molecule, etc. But if the coupling becomes strong enough, I really get into the regime where this square root becomes positive. I get two new energies. I get kind of a so-called vacuum Rabi splitting here, and the eigenstates of the system become really superpositions of an excitation on the molecule and the photon in the cavity. So these are dressed states or polaritons, as we call them. And if you think of this in a temporal picture, it means that, for example, if I start with an excited molecule, that's really the superposition of these two polaritons, the upper polariton and the lower polariton. And if I involve it in time, it gives me the so-called vacuum Rabi oscillations, which really means that the molecule emits a photon into the cavity and reabsorbs it and re-emits it, etc. And vacuum, because this is not driven. I don't need any field here. So I really don't have any external laser field. Okay, so and this can be done in experiments. So what you see is exactly that in the kind of here they have a molecule that is aligned orthogonal to the electric field in this nanocavity in this case, and you basically see just the absorption of the nanocavity or the scattering. And if you bring it into strong coupling, you really see this strong coupling between the molecule and the cavity mode, which in this case is a plasmonic nanocavity, and you get a very strong splitting of the absorption. And so you're really changing the levels of the molecule and of the cavity in some sense. And why you want to use organic molecules for this? Well, first, originally, they were used because they have large dipole moments. You can pack them quite densely, so then you get actually collective enhancement. So instead of a single molecule coupling to a cavity mode, if you put a lot of molecules in there, you get kind of basically the Dix state coupling to the cavity, and that gives you an enhancement in the coupling strength that scales with the square root of the number of molecules. And interestingly, since we saw that the single molecule coupling is proportional to the inverse mode volume of your cavity, if you assume that you fill the cavity completely, it means that the Rabi splitting really becomes proportional to the density of molecules. And that means that you get roughly the same Rabi splitting in very different physical systems. And that Rabi splitting can reach more than 1 electron volt. So you get the Rabi splitting of, in this case, the first experiment that did this was in '98, in a relatively big kind of Fabry-Pyrrhot cavity with a silver mirror and a DBR mirror. And they filled it here with these dye molecules. And you see as a function of the angle, which is the in-train vector, you see these two peaks where you see a nice Rabi splitting. So the dashed line and the solid line would be the cavity without the molecule or the molecule without the cavity, and then you get here these two polaritons. But it also works with light modes that are a lot more confined. For example, these surface plasmons that are confined light modes propagating along a metal surface. This is essentially the same picture as here as a function of angle. You see this Rabi splitting with the two peaks. Or it works even in the limit of kind of these extremely tiny nanoscale plasmonic cavities where you have mode volumes of some tens of cubic nanometers is the record, I think, where you get to the strong coupling regime even with a single molecule, or with a few molecules at least. And this is at room temperature, I should point out, so you have really long, strong losses. You have lifetimes of typically femtoseconds of these plasmons, so these are really wide modes. This is not kind of atomic physics megahertz lines, this is 100 millielectron volt lines or 30 millielectron volt lines. And the Rabi splitting, since it is so large, you still get into this regime, and you still get these polaritons. Okay, so why do you want to do this? Why are you actually interested in this? Well, first, the first applications kind of really used that as hybrid light matter states, the polaritons inherit properties from both constituents. So they have kind of from the light extremely low effective mass in the cavity, if you have a cavity where they can propagate, and they gain from the molecule, for example, mutual interactions. And since these polaritons, if you have a big system, behave effectively like bosons, they can actually condense. And you get Bose-Einstein condensation, which was first shown in inorganic semiconductors, where it's not molecules, but Wannier-Mott excitons that are used. So this was 10 years, or a bit more than 10 years. And then a few years later, they showed it in organic molecules as well. So you can really get a macroscopic population of these hybrid light matter polariton states. Another thing that you can do is you really think about I'm modifying energy levels, and I'm really modifying kind of the molecular dynamics. So if I look at something like first the resonance energy transfer from a donor to an acceptor, usually we know that works over length scales of maybe 10 nanometers. But by putting this into kind of the states into strong coupling, I'm generating polaritons that are in this case collective because they couple to light modes that are distributed over the whole cavity. So I can put the donor here with a space of a few hundred nanometers in between even, and then acceptor molecules here. So in this case, I'm coupling 3 levels. So I couple the donor excitation, the cavity, and then acceptor excitation, and I get 3 polaritons instead of just 2. An upper polariton that in this experiment, they set it up in such a way that the upper polariton is basically donor molecules, a middle polariton that is kind of mixed, and the lower polariton that is basically only acceptor molecules, just because of the coefficients of the eigenstates here. And so what they see here is that now if you pump the upper polariton, you see quite strong emission from the lower polariton, basically meaning you pump the donors and you see strong emission from the acceptors. So you get energy transfer from donor to acceptor molecules over a length scale of 200 nanometers or something like that. And interestingly, we've worked on this theoretically in the last year, and what we found is that really this decay, interestingly, is driven by local vibrations. So it's the decay from the upper polariton to the middle polariton and down to the lower polariton that drives your energy transfer, but this is not kind of coupling that makes the energy jump from here to here. This is coupling that makes the state decay locally by photonic decay. So the system emits a photon, but that now couples between my polaritons. So the upper polariton was only a donor. The middle polariton contains both. Then through another phonon decay, I go down to the lower polariton and I have only acceptor, and then kind of I'm never jumping from one to the other. I'm just coupling locally, and I still get non-local energy transfer. So I think that's very interesting. And the last thing I want to talk about is chemistry. using this for chemistry. So if you put a molecule into the cavity that can undergo a chemical reaction, in this case, for example, isomerization, they showed that kind of by doing this, here the spiropyran form has no resonance where the cavity mode is. This is again as a function of in-plane momentum of the cavity. And they drive this isomerization reaction with ultraviolet. And once it's in the merocyanine form, you can turn on the strong coupling, in this case, with 700 millielectron volt Rabi splitting. So you can really reversibly switch on and off the coupling. But the more interesting thing there is that if you now look at the reaction rates of exactly this system in the cavity, you find that they're really significantly modified depending on whether you're inside the cavity or not. So you've modified the chemistry and the chemical reaction here, and the big question is why, what's happening, and how can I describe this? So we have been working on this, and I don't want to talk too much about our results, so I'm just putting them here in the introduction as well. But we've showed that you can, for example, really suppress photochemical reactions very strongly. We've showed that you can even make up a kind of a setup where you use a single photon and you get a chain reaction in all of the molecules to kind of trigger photoisomerization in many molecules at the same time. And I don't want to go into detail because this is supposed to be about computation, but I think these are very interesting applications. And I just want to mention that kind of this suppression of a reaction has been shown now very recently in an experiment by the group of Timo Shegai. And they see that kind of basically by putting the molecule into strong coupling, they can strongly suppress exactly, in this case, photooxidation. Okay, so what are the challenges for theory for this? Well, we have to deal with molecular physics and chemistry of relatively complicated molecules, and we have to deal with nanophotonics or plasmonics with quantized light modes. And we want to combine this to do what we call organic polaritonics or polaritonic chemistry. So I have the problem that I have, first of all, mostly photochemistry, so I have to be able to calculate excited states of the molecules well. I have relatively big dye molecules, or even proteins, and they have even done strong coupling with living bacteria. So you can go to really big systems. This is usually in solid or solution at room temperature, so you have very fast dissipative baths. So you need to do kind of open quantum systems. And you have many molecules, so a macroscopic number of molecules that are included. In addition, you have here for the nanophotonics, you have to take into account that you have really strongly lossy modes, especially for the plasmonics that you want to do for doing few molecule strong coupling. You have loss rates, as I said, on the order of tens of femtoseconds. So this is really tricky to kind of get right, and especially how to quantize lossy modes is still a kind of open question if they're so lossy. You have to take into account that you have relatively complex near-field distribution, so you have to deal with all of the complexity of nanophotonics. And you often have not just a single light mode that is important, but you have a kind of continuum, or you have in plasmonics a lot of very near-field modes. And kind of this, of course, makes it also more complicated. And in the end, kind of this is not so much a challenge, but makes it harder to do just a single theory is that you can, since this is photonics, you can kind of think of any photonic structure you want to achieve the results that you want. So you have a large freedom of design and a huge amount of different photonic structures you might want to treat. And so if you wanted to code to do this, you would need what you call in German the egg-laying wool milk pig, so that can do everything that doesn't exist, unfortunately. So, well, we have to do with something smaller, but we're trying to get there. So if to go back now to say what is really the Hamiltonians we want to treat, now I'm going to just, for a single molecule with a single light mode, the extension to many molecules and many light modes is kind of obvious anyway. So we have as the Hamiltonian, kind of the molecular Hamiltonian, and then the photon and the photon-molecule interaction. Here I'm already assuming that we know how to quantize the light mode, and we say we have only a single one that is important. So in that sense, I mean, this is kind of the standard molecular Hamiltonian that we always have. The light mode is just its energy, and then I have the coupling where I have here the dipole-dipole interaction, and interestingly, in this quantized limit, and if I have really very strong interactions, I sometimes also have to take into account this so-called dipole self-interaction that has here the electric field of the cavity mode, but actually no cavity operator. So this depends on the gauge. If you go to the other gauge, you get here A squared, which is only the field, but it includes the dipole moment of the molecule. In this case, you get here the dipole operator, and this can do also significant changes. Also on the ground state, I should mention, not just on excited states. So if I want to do theory, how should I represent an organic molecule now? Most applications kind of up to a few years ago just treated them as two-level systems, like I do in cavity QED, and this works for a lot of things, but of course doesn't include any internal structure or chemistry or anything of that kind. So the next kind of step is to say, okay, I take into account that I have quite a few states in the molecule, I might have triplets, I have losses in between them, and I take into account the vibronic mode, the vibrational modes, at least as a set of harmonic oscillators, which works a lot, gives you a lot more physics, let's say, as long as the molecules stay more or less close to equilibrium positions. And then in the end I can say, okay, I just do full quantum chemistry and let's see what happens. So this is basically what we have been kind of trying to work on. In the first step, we said what we found is that we can actually use a lot of the concepts of quantum chemistry and of the Born-Oppenheimer approximation also under strong coupling. So what we found is that we can understand a lot of the physics or chemistry of these systems by following nuclear motion, not on the traditional potential energy surfaces, but on polaritonic potential energy surfaces. So if I take a very
rest state.
Yeah, so I'm going to explain this right now. So if I assume that my molecule just has a ground state and an excited state with just a single reaction coordinate and they're a bit offset, if I put this into the cavity and I now have weak coupling, basically my photonic excitation, I don't have just the electronic excitation, I also have the possibility to excite with a photon, and that doesn't affect the molecule if I'm in weak coupling. So I just get a shifted copy of the ground state potential energy surface, and now I can turn on the coupling, and that actually becomes a coupling between these two surfaces, and I get new potential energy surface that are then obviously kind of straightforwardly, we can call them the lower polariton and the upper polariton potential energy surface. And what I'm doing really is kind of solving the same 2x2 Hamiltonian that I had before, but just now resolved in space. And this doesn't have to be in one dimension, and it doesn't have to be harmonic oscillators. So the kind of the results I showed before were using 1D model molecules. I wanted to say, so kind of the idea of this is we don't want to guide the way, we don't want to do coherent control and pump the system from one spot to the other. We want to change the roads, change the surfaces. So before we were using 1D model molecules, and then we said, okay, let's use that we have this and that we can do kind of classical chemistry and couple it. So we have developed this approach kind of inspired by photochemistry that we have called QED-MM, which is basically using standard quantum mechanics, molecular mechanics that people do in photochemistry to represent the molecules. And here you can include the solvent, you can include big molecules relatively straightforwardly, and then you do classical nuclear motion on these new surfaces, and you include non-adiabatic transitions, so surface hopping. And there we could really make use of existing software efforts in the community. Actually, we're collaborating with one of the developers of GOMAX, Gerrit Grönhoff. And the nice thing is that it has interface to standard quantum chemistry packages for doing QMMM. So we're actually now using TerraChem, which is this GPU-accelerated software, which works really quite a bit faster than standard quantum chemistry methods. And the nice thing is this approach is very easily parallelized, because I can do each molecule by itself and just couple kind of the final Hamiltonian is just an n by n Hamiltonian as long as I stay within the single excitation subspace. So we've, for example, done 1,600 rhodamine molecules where the full calculation contained these, to me, kind of absurd numbers of atoms and 38,000 CPU cores. So this is really Gerrit who wrote this code. And it works, let's say. For example, we have here a simulation of the bare molecule that would undergo photoisomerization if I excite it. So I started with the photon and now it did this rotation. And if I put this into the cavity, and in this case I need a few of them because this is also a collective effect, and I start the simulation, you will see that it's very boring because basically nothing happens. So I can really suppress photoisomerization here by putting the molecules into a cavity. But just very quickly I want to point out, with this classical dynamics approach, we don't get quantization of the vibrations. So we don't get actually resonant transitions between the polaritons, which are known to be important in the experiments. And so to kind of get around that, we have been working on an approach using a tensor network tree tensor network, or matrix product states, if you want to present really the full quantum mechanical wave function. So very similar to what Agavan talked about. The only problem or restriction for now is that these are only harmonic oscillators for the nuclear degrees of freedom. So it works if we're close to the equilibrium position. And this is really, for me, an amazing method, because you can do full quantum simulations of a system with, in the end, I think 3,000 degrees of freedom on a single node. And we get the full kind of quantum solution on a single node.
The GPU.
This is no GPU. This is MATLAB. This is MATLAB even.
Okay.
So this is codes that a guy in the group of Alex Chin developed. And we use here this chain mapping. That is a very smart way to kind of transform a vibrational bath of many modes into a chain that then is 1D. So this is kind of ideal for matrix product states. And we get, I don't want to really talk about the results, but we see that we have kind of a lot of results or a lot of effects in this system that are clearly non-Markovian, so we cannot really just treat the phonons as a bath. We see that we cannot just restrict the system to a single phonon description or a single reaction coordinate description, and we get a lot of coherent oscillations between the nuclei or the phonons and the electrons and the photons. And so to finish, I think I tried to show that polaritons and polarity chemistry are really novel tools to manipulate material properties and molecular structure, and we need much better software, I think, to solve this. And there's still a lot of things to do here, and I want to thank all of my co-workers and funding agencies. And I just wanted to point out very quickly that we're organizing a summer school on manipulating light and matter at the nanoscale in Madrid in September. So if anyone is interested or has students that might be interested in this, please feel free to come. And if you know anyone who's looking for a postdoc, please tell me. Thank you.